In this video, we'll take a look at optimization problems. Ever since calculus was invented, or was it discovered in the 17th century by Newton and Leibniz, calculus has been used to solve optimization problems. But what is an optimization problem? In mathematics, computer science, medicine, and business, an optimization problem is the problem of finding the best solution for all feasible solutions. In mathematics, you might be asked to find the maximum size container you can make out of the smallest amount of materials. In business, you might be asked, what is the optimization cost to give you the best profit? I can remember when I was at university, I wanted to know what is the best amount of sleep to have in order to maximize my test scores. The graph might have looked something like this, where the test score is mapped against the sleep in time. Here, no sleep at all, zombie score. Here, it might look like you've just got enough. Here is a great score. But as you can see, after the great score, your test scores start to go down. This is because too much sleep means not enough study. In business, you might look at the effect that price has on profit. So you might draw a graph of price against profit. And as you can see from this graph, as the price increases, initially the profit also increases until it reaches a maximum. Then, as price increases, the profit starts to decrease. If you draw a tangent at the ideal price, which is a maximum, you can see that the gradient here is equal to 0. Another type of problem we might be looking at in business is to minimize cost. So what are the minimum costs to maximize our profits? Here we would be looking for a minimum point, not a maximum. Let's do some questions. 1. A company manufactures tins in the shape of a cylinder with a constant volume of 150 pi cubic centimeters. In order to minimize costs, the company wants to minimize the surface area. A. By expressing the height h of the tin in terms of its radius, show that the surface area is given by S is equal to 2 pi r squared plus 300 pi over r. If we take any cylinder of radius r and height h, we know that the volume is equal to pi r squared h. We are told in the question that the volume is equal to 150 pi. Therefore, we know 150 pi is equal to pi r squared h. We can rearrange that to give us h is equal to 150 pi over pi r squared. Therefore, h is equal to 150 pi over r squared. The volume for surface area is equal to 2 pi r squared plus 2 pi RH. We know what h is, therefore S is equal to 2 pi r squared plus 2 pi r times 150 pi over r squared. We can do some cancelling, and we are left with S is equal to 2 pi r squared plus 300 pi over r, which is what we want. Part B. Use calculus to find the minimum value for the surface area of the tins. Give your answer correct to 2 decimal places. We know that the surface area is equal to 2 pi r squared plus 300 pi r to the minus 1. So to get the minimum, we need to first differentiate. So ds over dr is equal to 2 times 2 is 4 pi. Take 1 off, so you get r. Minus 1 times 300 is minus 300 pi. Take 1 off, so you get r to the minus 2. Therefore, ds over dr is equal to 4 pi r minus 300 pi over r squared. In order to minimize, we need to put the differential equal to 0, so ds over dr equals 0. Therefore, 4 pi r minus 300 pi over r squared is equal to 0. I'm going to multiply every term by r squared, so therefore I get 4 pi r cubed minus 300 pi is equal to 0. Therefore, 4 pi r cubed is equal to 300 pi. Therefore, r cubed is equal to 300 pi over 4 pi. The pi's cancel, so r cubed is equal to 75. So r is equal to the cube root of 75. Now I need to find s when r is equal to the cube root of 75. So I'll substitute s is equal to 2 pi times the cube root of 75 squared plus 300 pi over the cube root of 75. Use your GDC to solve this, and I get a final answer of 335.23 centimeters squared as the minimum surface area for the tins. Question 2. A population of rabbits is modelled over the course of a year by the function f of t is equal to minus 1/8 t cubed plus 11/5 t squared plus 20 over the interval of t between 0 and 12, where t is the time from the start of the year in months. A. Find the population of rabbits at t equals 8. So we want to find F8, which is equal to 1/8 times 8 cubed plus 11/5 times 8 squared plus 20. So F8 is equal to 96.8. So F8 is equal to 97 rabbits to the nearest B. Find the maximum population and the time at which it occurs. We know that f of t is equal to 1/8 t cubed plus 11/5 t squared plus 20. To find the maximum, we need to find f dash of t, which is equal to 3 times minus 8 is minus 3/8 t squared. 2 times 11/5 is 22/5 t. We put f dash of t equal to 0, therefore minus 3/8 t squared plus 22 over 5 t is equal to 0. We have a quadratic which can be solved using the TI Inspire. If I open the TI Inspire at a calculator page, I'm going to use the polynomial solver to solve my quadratic. So I go to Menu, 3, 3. I want to find the real roots, so 1. It's of degree 2 because it is a quadratic. So OK. Now I can type in my unknowns. So the first one is minus 3 over 8. B is 22 over 5. C is 0. Press OK. So there's my polynomial roots over. Press enter. And I get two values, 0 and 176 over 15. Well, I want to convert that to a decimal. So I go to number, convert to decimal, press enter. So my two values are 0 or 11.7333. Well, it can't be 0, so it has to be 11.733. Now I want to find the y value at x equals 11.733. So if I go to another calculator page, I've already defined my function, which is minus 1 over 8 x cubed plus 11 over 5 x squared plus 20. So if I now type in f 11.7333, press enter, I get 120.959. So the maximum population is equal to 121 rabbits, and it occurs after 11.7 months. Part C. Find the value of t for which the population is increasing most rapidly. In order to do this, I need to graph f dash of t and find the maximum. So I'm going to go back to my GDC. So I've opened the graphs page. Earlier I'd already defined my function, so now I want to draw the differential. So if I go there, open the differential, it's x. My function was called f of x. If I press enter, there is my graph, but I can't see it all, so let's move that out. I'm going to go to menu. I'm going to go to Windows and zoom to fit, and there is my graph. I can clearly see where the maximum is, so I'm going to find it. So analyze graph, maximum, slightly to the left, now to the right. So my maximum occurs when t equals 5.87 and has a value of 12.9. To answer the question, the population is increasing most rapidly when t is equal to 5.87 months. Question 3. A model rocket is released from the ground on a vertical trajectory. The height h in meters that it can reach is modelled by h is equal to 2m squared over 15 minus m cubed over 480, where m is the mass of fuel in grams. Find dh over dm and simplify it. So dh over dm is equal to 2 times 2 is 4 m over 15 minus 3m squared over 480, which is equal to 4m over 15. 3 and 480 will cancel to leave us with m squared over 160. Part B. Using your answer to Part A, find the mass of fuel that is required to reach the maximum height and state the maximum height. Well, we know that dh over dm is equal to 4m over 15 minus m squared over 160. In order to find the maximum height, we need to put dh over dm equal to 0. Therefore, 4m over 15 minus m squared over 160 equals 0. I'm going to use the TI Inspire, draw the graph and find its maximum. I've opened my TI Inspire at Graphs page. I've got a rough idea of what values I'm expecting, so the first thing I want to do is change my window. So I want it x direction to go from -1 to 50, and I want the y direction to go from -1 to 100. So that's my new window. Now I'm going to type in my function, which is 2x squared divided by 15 minus x to the power of 3 divided by 480. Enter, and there's my function. I can clearly see there is a maximum around this area. So I'm going to go to Menu, Analyze Graph, Maximum, somewhere to the left, to the right, and I find that my maximum is when m is 42.7 and the rocket reaches a height of 80.9 meters. The final thing to do is answer the question. So, H max is equal to 80.9 when m is equal to 42.7 to 3 significant figures. Question 4. A farmer wishes to enclose 2 fields. At the farm, he has a natural barrier, a canal. He has 200 meters of wire. He needs to ensure one field is twice the size of the other. What are the dimensions of the 2 fields? First, let's draw a diagram. So, there we have our canal. And we want 2 fields. and we want one to be twice the size of the other. So I'm going to let the width of the first field, we'll call A, be x. So that means the second field has a width of 2x. We now have 200 meters of wire, and we got 3 lengths still to build. So each length must be 200 minus the 3x divided by 3 meters long. So we've now got 2 fields, A, and we'll call the second one B, and I'm going to work out the total area for those 2 fields. If I expand these, I get the area will equal 200x over 3 minus 3x squared over 3 plus 2 times 200 is 400 x over 3 minus 6x squared over 3. Therefore, the area is equal to 600x over 3 minus x squared minus 2x squared. So the area is equal to 200x minus 3x squared. I want to find where this area is maximized, and I want to find what value of x gives me the maximum area. In order to do this, I'm going to use my TI Inspire GDC. I've opened my TI Inspire to a graphs page. I've already changed the window. So x is going from 0 to 100, y is going from 0 to 4,000. Now I'm going to type in my function, 200x minus 3x squared. And there is my function. I can clearly see that there is a maximum around here. So I'm going to find that maximum. So menu, analyze graph, maximum, to the left, to the right, and I can clearly now see that there is a maximum when x is equal to 33.3, and that gives me a value of 3,333. Make sure you answer the final question, and it wants the area, so the area of small field is 1/3 of 3,333, so which is equal to 1,111 meters squared, and the area large field is equal to 2,222 meters squared.